Hey guys, so today we're going to talk about compound inequalities and the applications of inequalities. This is 2.05 and 2.06. So compound inequalities are regular inequalities, but compounded with the word and or. That means they just kind of go together. So if we had x is less than 2 and x is greater than negative 17. So if we go to draw this on a number line, then we're going to graph each of these. So we've already learned how to graph inequalities. So we're going to do x is less than 2. So I'm going to put 2 over here. And I'm going to change colors right quick. And we're coloring in all of this. So now say negative 17 is right here. I know that this isn't drawn to scale, but forgive me. And now we're trying to graph the second one. So I'm going to graph this one in purple. So x is greater than negative 17. So we color in and we go all this way. So this looks like what we've known before in regular inequalities. I also need to put my open circles. So for regular inequalities, this is what we've already learned. It's just how to graph things individually like this. But what this and means is we need something that is this and this. So the blue is what fits in here. And then the purple is what goes here. So we need something that is blue and purple. So we're trying to pick a zone that is both blue and purple. And that's just going to be this zone. So our solution could be anywhere from here all the way down to here. So this is a compound inequality. What your homework looks like on this, something like x is less than 5 or x is greater than negative 2. And it wants you to talk about this in actual words. It wants you to convert it. So it gives you several options, and you can think of x as all numbers. So you could say all numbers less than 5 solves this. So I'm going to write that. Or, and now we read the second part, all numbers greater than negative 2. So I'm just going to put the greater than negative 2, or negative 2 if we write it all the way out. So this is how you go about converting some mathematical statement like this up here into actual words. So we look at it and we say all numbers less than 5 or greater than negative 2. So with or instead of and, we're not looking for overlap necessarily. We're just looking for where they fit on the graph. So if we have a 5 over here and 4, 3, 2, 1, 0, negative 1, negative 2. So if we are going to graph this, then we're going to put x is less than 5. So I will color that with green. So we are coloring in, and it goes all the way this way. It doesn't stop at 2. Because x can be anything less than 5. Or, we'll go red for this one, x is greater than negative 2. So if we start at negative 2 and we start coloring this way, well, anything on the red section can fit this second part. So it doesn't necessarily have to be both. Like earlier we were looking for overlap. For this it can be either one. So we have pretty much the entire number line is colored in. We've got this part's covered by the green section, this part is covered by both sections, and this part is covered just by the red section. So with or, you just graph them both, and that's your solution. It's anything that's colored in. But with and, you have to look for this overlapping section like this. So working a couple more of these types of problems, sometimes we may actually have to work them out or do some work to get them down simple enough to graph. So for example, we could have 2y minus 7 is greater than 1, or 4y plus 3 is less than or equal to 5. So the way that I like to solve these is I will draw a big dividing line down the middle of my or, just so that way I know that I don't need to worry about it right this second. I can deal with just the left side, and then I can deal with just the right side. So when I deal with just the left side, my goal is to get this y, the variable, by itself. It could be x, it could be m, it could be anything. So when we try to get it by itself, we add our 7 across. That cancels out. We end up with 8. 2y divide by 2. We end up with y is greater than 4. And over here we do the same thing. So we subtract our 3 minus 3. That goes away. We end up with 2. And 4y is less than or equal to 2. So when we divide, we're supposed to divide by 4. Divide by 4, divide by 4. This goes away, and this turns into y is less than or equal to 1/2. Okay, so now is when we can look at our or. So I'm going to put it back and circle our problem. So now our goal is to graph this. So I'm going to draw my number line, and I'm going to put points on it. I'm only going to put the important points. So we have 4, and we have 3, 2, 1, and 0. So we know that y is greater than 4 because the alligator is eating the y, so it's the bigger number. So I will color that in orange. So we're going to color this way. And I'm going to use my open circle because if you will remember, open circles go with these guys and closed circles go with these guys. You can remember that by extra mark, extra dark. So now in blue, we're going to do this one. So we have y is less than or equal to 1/2. So if we say 1/2 is right here, we're going to put a closed circle because extra mark. And we're going to color in everything this direction. And because we have an or up there instead of an and, this is our solution. Anything all the way to the left of this graph, so anything from negative infinity to 1/2, and then starting up again at 4 and going all the way to infinity. So these are the important numbers. Anything between these two and anything between these two. So sometimes you will have to solve down and get it simpler so you know how to work with it, just like we did in that problem. So working one more example. If we have something that looks a little different, we can have 2 is less than m over 6 is less than 3. So this looks a little different because we don't have an and or an or, but really this is an and problem in disguise. This says 2 is less than m over 6 and m over 6 is less than 3. So all I did was just write this twice and work it that way. And if you want to convert these over to these, then that's fine. But I think this is a little easier to look at once we've talked about it. So we treat these like equal signs, just like we do when there's only one of them. So anything we do to one side of the equal sign, we have to do to the other sides of the equal sign. So to undo this multiplication here to get m by itself, which is what we want, we need to multiply by 6. So we multiply by 6 over here, and we multiply by 6 over here. So we end up with 12 is less than m is less than 18, which is true, or it can be true. 12 is definitely less than 18. This needs to go in order. Most negative to most positive, or smallest to largest. So if we put this on our number line, what this means, more or less, is m is between 12 and 18. So I'm going to put 12 here, and I'm going to put 18 here. And instead of drawing everything like I would over here, I can just go directly and draw my line between 12 and 18. And then I use my signs here to determine whether I use an open circle or a closed circle. So in this case, it looks like I'm only using an open circle. So that's how you deal with compound inequalities. Remember your divide by a negative rules still apply. If you divide by a negative number, you have to flip the sign of the inequality. So keep that in mind as you're working these yourself. So moving on to 2.06, this is mostly word problems for inequalities. So if we do something like this problem, I'm going to write it down. So a car salesman is paid $50,000 per year, plus 10% commission on all sales. How much would he have to sell to make more than $100,000 per year? So if we set this up, I like to work backwards on these, or problems that are set up like this. So he needs to make more than $100,000 per year. So I'm going to write $100,000, or just $100,000. And he wants to make more than that. So we want whatever is on the other side of the inequality to be greater than 100,000. So now we look and we say, okay, he makes 10% commission per sale. So if he makes 10%, then we know that he is making 10% times how many ever sales he makes. And he's also making $50,000 per year, regardless of what he sells. So we're just going to add that on top. So $50,000 plus 10% times X, which is X would be the number of sales that he makes, is greater than $100,000. And we can go and solve this to figure out how much he would need to sell. So what we do is we try to get X by itself. So we subtract $50,000. Subtract 50,000. These will cancel out. And now we have 10% times x. So we divide by 10%. And 10% is often written as a percentage, but when you work with it, you need to work with 0.10, because to convert from percentages into numbers that you can multiply and divide by, you need to take this decimal point and move it to the left 2 places. So if we have 10.0%, then we take the decimal point and it just jumps 2 places to the left. So we end up with 0.10, or just 0.1, which is the same thing. So I'm going to erase this 10% and put a 0.1 there. So we need 0.1 and 0.1. I'm going to erase it here as well just to make it a little clearer. 0.1. So these 0.1s are going to cancel. And now we're dividing $50,000 by 0.1, which I will plug into a calculator. So we end up with x is greater than $500,000. So the car salesman needs to make more than $500,000. He needs to sell more than $500,000 to make $100,000 in a year. So now that we've solved that, this is honestly a pretty standard problem from this section. Most of them are just setting up the problem with word problems. And once you've set them up, then you just evaluate the inequality by getting x by itself or getting your variable by itself, and then the answer presents itself. That's what you're solving for when you get x by itself. So with that, I'm going to end this here today. Have a good day, and I will see you soon.